Here's a resistor right here. You can see there are molecules inside the resistor, and now we're going to send some charges through. We're going to create a current. The charges are in blue and they travel across, but they don't just go straight across, they bump into the molecules, and so they find this kind of circuitous path. There's some slow speed at which they drift through the resistor. That speed shows up in a really important equation. I equals NAQV. I is the current in the resistor. Q is the charge of the carriers. In real-world wires, electrons are what move. And in that case, Q would be 1.6 times 10 to the minus 19 coulombs. What about N, A, and V? Well, V is just the drift speed. It's that slow speed at which charges drift across the wire. N and A are a little bit trickier to understand. So imagine you take your wire and you cut it right down the middle. The area that you expose is called a cross-sectional area. Cross-section just means you've cut straight down the middle across the wire. You're not cutting at an angle. So A is the cross-sectional area. And what about N? You might think N is just the number of charge carriers, the number of electrons in the wire, but it's a little bit more complicated. Here are the charge carriers flowing past. If you were to cut out 1 cubic meter, like this, and you counted inside that cubic meter, what's the number of carriers per cubic meter? Well, I've got 1 here, there's a second, here's a third, 4, 5, 6, 7. Did I count that right? N would be 7 per meter cubed. Now, in reality, the value is much, much higher, but this just illustrates N is the number of charge carriers per unit volume. And in physics, we are going to be using meters cubed as our unit of volume.